This is lecture number 10, 10th lecture on the topic 8, which covers the converter modeling. And the subject of this lecture is small signal model of PWM converters. So we went through all the details about the power stage model and the modulator gain, describing function representation of PWM block. And the remaining task is to incorporate those models with the small signal model of voltage feedback circuit to yield the complete converter model, small signal model of PWM converters. So first, let me highlight the content of the previous lecture. Previous lecture was about the modulator gain, high frequency characteristic of the modulator gain, and the result is shown here in the form of impact of this modulator gain or describing function of modulator gain on the loop gain characteristics, magnitude and the phase of loop gain TMS. Okay, the purple color is the theoretical prediction of small signal model you will be seeing in the textbook. Okay, and the other one is this red curve is the actual measurement or actual simulation based on the time domain computational method and magnitude curve and phase curve and also prediction of Dr. Middlebrooks paper. So there are some differences here, and big differences at high frequencies. Okay, so this noise at low frequency comes from the practical limitation of measurement or simulation, time domain simulation of converter at low frequencies. So this is the impact of noise. So you can ignore this. And difference in this mid frequency is coming from the difference in the quality factor of double pole. So this is the CCM case. Okay, we are talking about the CCM only. Okay, DCM will have something similar to this, but we are not interested in DCM because when designing the converter, we only consider CCM. I explained the reason for that. Okay, so this difference is coming from the difference in the damping. So in practical situation, this damping, assume this red one is measurement, then damping will be reduced due to the unaccounted parasitic resistance existing in the hardware, and at high frequencies, the magnitude will show this. This will apparently appear in the measurement, okay, predicted from the describing function of this modulator. So you will see this. If you have good impedance analyzer, you can see this, okay? And this phase delay at high frequency is very, very common, okay? For the most time domain simulation, computational method or measurement, you will be observing this. So there is just some additional phase delay, and this red curve is measurement, and this purple color is a small signal prediction, okay? So this is about the modulator gain, and this, so you don't have to be surprised seeing this in your measurement or in your simulation using time domain computational method. This is the thing existing at high frequencies, okay? But this low frequency approximation of this modulator gain as a constant is only valid for the frequencies well below this switching frequency or have the switching frequency. Okay. Okay. Remaining job is to discuss about we combine everything to form those small signal model of complete PWM converter. Okay. So before that, I'd like to address this. So difference between the block diagram model of conventional feedback system you have seen in the textbook, which is something similar to this, and the small signal model of converter, which is something like this, something similar to this. Okay, so they look different, but basically they are the same thing, but it looks different because the unique characteristic of PWM converters. PWM converter is also negative feedback controlled system, but it's very simple form or special form of feedback control. This is a general form. Okay, this conventional feedback system. Suppose this is the motor drive something or motor and some electric vehicle, gear train and this wheels and so on. So this is the plant. Okay, you sense plant and fed back to this and you compare with this the command. Okay, command is the desired your desired intention. This machine will be handled. Okay, like the increasing speed or changing direction. So this is the command, and you have compensation here. So this is the compensation. Okay, and the G2 is here, and the G1 is here. Okay, this is inverting amplifier, and the ratio of magnitude of this divide this and this evaluate at DC becomes infinity. This output will be regulated at this value, exactly this value, because this is the unit feedback system, okay, and this command, okay, and this is some perturbation. Maybe you are driving car, but there is a uphill, then this torque will be increased. So maybe this can be step increase, torque, step increase in torque, something like that. And this is the conventional feedback block diagram of the system. You have seen this many times in the control book. Okay. When I was studying this power electronics, I saw this, and it looks different. Okay. And where is the input? Where is the output? It's not a pattern. Here, there is a reason for that, because in the feedback system, we don't have this control input. Control input is 0 in terms of the AC response, because this control input is this V reference, and V reference is fixed. It's always fixed. You want to keep this fixed as closely as possible. So in this block diagram, there is no input command. No, there is no input port or the port corresponding to this, and you don't have this is called the summer. You don't have the summer here. Okay. Then what you have is this. This is the disturbance in the input voltage, and this is the disturbance in the load current, and D is control variable, small signal change in Dewey ratio. Okay. And this is a small signal change in the out voltage. Oh, it's not okay. Here, this is a small signal component of our voltage is fed to here, and this is the voltage feedback circuit, and transfer function of this G2 divided by G1 with minus sign in front of that is called the voltage feedback circuit, and this will be gone. When we are considering this we consider this DC voltage source is showed. Then this is the small signal control block diagram of PWM converter. So this looks different, but basically they are same thing. Again, this PWM converter is a simple form of feedback system. There is no command input. There is no command to follow. What we have is just disturbance, control variable, and this out voltage. Okay. So we don't need this summing block. So there is no summing block. And if this part is replaced with this functional representation, then this becomes the complete and legitimate small signal model of PWM converter. So in the following lecture, we'll go through some details about this. Okay. So somehow I thought this is necessary because I was confused in the past. I was confused a lot. I thought the input of converter is the input variable. Okay, that is true. Okay, in some sense, but it's not easy to see that input voltage is grounded always. This is grounded. Okay, then you can simplify the whole thing to this simple diagram. Okay, you will see that soon. The topic of the last class is small signal model of complete PWM converters. Okay. So now we start the last lecture. Subject of this lecture is small signal models of complete PWM converters. So I have one slide prepared maybe 10 minutes ago. So this is the functional diagram of a closed loop PWM converter. So you have power stage, and you have PWM block, and you have voltage feedback circuit. And in the previous lectures, maybe 2 weeks, something like that, we finished the small signal modeling of power stage and PWM modulator. So this is the summary of that. So PWM power stage is modeled as PWM switch model, and this PWM switch model is applicable 3 basic converters. So maybe this originally presented here can be classified as the basic model or simplified model. Okay, so or just PWM converter model, and to extend the application of that model, we considered 3 cases. And the first case is the case with parasitic resistance of the reactive component. And the second case, we considered this isolate converter cases. And finally, actually we did this first DCM operation of the converter. So for this case, we derived the defined PWM switch model. So it includes one resistive component, and the coefficient of dependent voltage source is modified. Okay, but we conclude that impact of that is very minor, can be considered negligible. So using this is okay. The simplified PWM switch model can be applied all the PWM converters with even the parasitic resistance. Okay, there are not much difference between exact model prediction and simplified model prediction. But you should know this. Okay, so when you have a chance to simulate this PWM switch or PWM converter, it's better to use this defined PWM switch model. Okay, so very minor changes, and isolate converters directly can employ the PWM switch model with very minor modification, maybe the parameter scaling with the turns ratio of transformer. Okay, and the transformer can be merged. Isolation transformer can be merged with the transformer in the PWM switch model. So basically, they are the same, and the DCM operation is substantially different, and we derived the DCM PWM switch model. Okay, so but you don't have to remember all the derivation steps, but you should remember this, that in DCM the system becomes first order system like. It presents first order system like dynamics, because in the CCM there are one double pole, and that double pole will be split into 2 dual poles, and one pole is going out of the picture. It goes to very high frequencies, and the remaining pole moves to low frequency. So basically the system is very similar to the first order system. Okay, and there are 2 resistive parameters which provide substantial damping. Okay, so system behaves as the first order system, but maybe you use this model to understand the dynamics of converter in DCM. You don't use this knowledge to design the converter, because you should use the dynamics of the CCM to design your PWM converter. Okay, so if the converter is properly designed for CCM, it also provides stability and some performance, which will be degraded somewhat, but still you are safe. Okay, the other way around, if you design your converter using the DCM dynamics, your converter surely becomes unstable when it enters CCM operation. So you understand this, but you never use this information for the design. Okay, for the design you should use the CCM model. Okay, so that was it. So power stage model, small signal model is completed, okay, for all type of PWM converters, including parameter, the parasitic resistance and isolation transformer, even in the DCM operation. Okay, and this block, PWM block, is very simple to model. The linearized model, very simple model, is just 1 divided by the magnitude of the lamp, height of the lamp. Okay, so it's called the linear modulator gain or linear PW gain. FM is 1 divided by VM. Okay, but this is a simplification. This might be good for the low frequencies well below the switching frequency of the converter. So for the exact prediction of high frequency behavior of this, we need to use this describing function method. So we didn't go the details about this. I just cited the result of this. So this is the describing function of PWM modulator, PWM block, so FM prime. And J omega is a function of the omega, and it is also a function of the magnitude of excitation signal, nonlinear term here, but it can be simplified with some assumption. So this H prime J omega is some stage function. Magnitude is this sync function, and it produces the delay at high frequencies. Okay, at the half switching frequencies, delay becomes 180 degree, and at the switching frequency, the delay becomes 360 degree with duty ratio of 0.5. Okay, if duty ratio is lower than that, the delay becomes smaller. Okay, it's a function of duty ratio, right? And this is apparent in the measurement and the computational method. But small signal model, you are using constant here. Okay, so this is ignored, completely ignored in the small signal model, and still, but small signal model is still useful if the loop gain crossover frequency is placed at significantly lower frequency than switching frequency. And you predict this additional fact, okay? And in terms of magnitude, the magnitude shows a deep, very deep, okay? Probably negative infinity dB at the multiple integer multiples of switching frequency. It starts from the omega s and the 2 omega s, 3 omega s. Okay? So with this knowledge, you are safe to use our small signal model. Okay? So, but you can observe this whenever you take the measurement and whenever you simulate using the computational method. If you use small signal model, you don't see this. Okay? This second order effect, or nonlinear effect, or time varying effect, or frequency dependent effect will be gone. Okay, but still okay, still safe. Okay, so the cautions of selecting the loop gain crossover frequency and the proper prediction of this additional phase delay is used, is considered. You are still okay, right? So remaining part is this one. So voltage feedback circuit is relatively simple because this is the linear circuit. Everything is linear. So this is just a simple linear circuit analysis or electronics analysis. But I'd like to have some discussions about this. Okay. The final small signal model of this complete converter looks very different from the feedback diagrams you are seeing in your textbook. Okay, they are same thing, but it looks different. So I'd like to address that aspect. So I prepared this. This is the small signal model of motor drive system, and later on I will present the small signal model of converter. Okay, the purpose of doing this is I'd like to use this as the comparative example. So I'll explain the similarity between them and also dissimilarity between them. Okay. So in the past, long time ago, when I was studying this for the first time, I got confused. Why the small signal model of PWM converter is different, very different. What I have seen in the control books. Okay, that was the big question, and I spent some time to figure that out. Okay, so I'd like to deliver that information. Okay, so this is the example motor drive system. I'm using this example. I used this in the control lecture, linear control system. I'm using this example. This is a very good example, easy to understand. All right. So let me explain this. This is the DC motor unit. Maybe you can consider this is applied for the electric vehicles. Okay. And this is called plant. Okay, factory plant. Okay, this is plant, and all of this is the feedback controller. This feedback controller consists of this is the difference voltage. So this is VCON is command control, command signal, and VSET is feedback signal, and this is the difference amplifier. Output of this is VLR is simply the difference between this minus this, okay? Because it goes to this positive terminal and it goes to this negative terminal, output this, okay? And this can be replaced with this symbolic block, okay? It's called the mixer. So this difference amplifier is simplified to this in terms of its function, and this is the error amplifier. So this is the non-inverting amplifier. Inverting amplifier, okay, very basic amplifier, and this is the DC motor unit. So this represent the dynamics of this DC motor. So inside of this, there is some internal feedback, and but you don't have to worry about this. Consider this whole thing as one functional block, and the output of this is the speed, rotational speed of this one, tire, okay? And this rotational speed is sensed by this tachometer, and that feedback signal is fed to the mixer, and that generates this error signal. It goes like this, okay? This is the typical feedback system. This is very good to understand because this is closely related with the drive and control system of electric vehicles. They don't use DC motor, they use some AC motor, and they use very strong permanent magnet. Okay, but still, this is a good example to explain the basic mechanism of this negative feedback control. Okay, so this is the story about the motor drive system, and this control block diagram is copied to here. So this is the same control block diagram. All right. So you have this. If the gain of this non-inverting inverting amplifier is this G2 divided by G1, evaluate at DC, there is a J0, okay, or simply 0. Ratio of this magnitude and this magnitude infinity, that means this one is infinity and this one is finite, okay, not infinity or not 0. Then this becomes 0, okay. So I'll explain the details about this in the next slide. So if this is infinity, then this V error becomes 0, okay. So that means this V error is the same as, this is 0, then this output of this tachometer is the same as this command signal. So you are closely regulating the rotational speed of the tire or speed of this vehicle. Okay, that is the command control. Okay, so this is the fundamental object of using feedback system. So this is called command tracking. This is the command. Okay, command tracking, and inside of this, there is some external or internal disturbance called the torque disturbance. Assume this is the vehicle, and the vehicle was running at constant speed, and there is a slope ramp. Okay, then this should increase the torque to have the same speed. Okay, think about the cruise control. Then this torque is increased. Okay, still then the speed of this vehicle must be the constant, and must be the constant here. So this function is called command tracking, and command tracking indicate this vehicle follows this speed command as closely as possible. That is the number one. And the other one is this output regulation, and this speed should be constant regardless of this the presence of this slope. Okay, uphill. All right. So this is the typical response due to this. So command signal is increased, then the speed of this vehicle it goes some overshoot, and it exactly follows this command, and the command is reduced, then the speed will follow this. Maybe there is some transient overshoot and undershoot. You want to minimize this. Okay, that is the one of your design goal. Okay, this is the conventional one. This is the general system. Okay, when people just talking control system, they are talking about this. Okay, and this is the something else. So here, this command signal remain the same or zero, but at this point, this torque disturbance is increased in step fashion because the slope is constant. Then slope is constant here. Okay, then torque is increased in stepwise fashion and decreased here. But during this transitional period, this speed omega s should be constant. Of course, you have some transient response here, undershoot because torque is increased, and now this overshoot because torque is decreased. Okay, so this is the one typical example of the concept of feedback control. Okay, and for this kind of system, maybe people are interested in three transfer functions, three closed loop transfer functions. One is this one. So multiplication of this. Okay, the transfer function of this inverting amplifier and this plant transfer function, and assume this the tachometric gain is 1. Then multiplication of all of this, which is this. Okay, so you have one negative sign here, and another negative sign here, and another negative sign here. Then 3 negative sign becomes it make the system negative. So you put additional minus sign because this whole thing should be positive. Okay, so this is called the loop gain, and this is used for the stability analysis. Okay, and also the closed loop performance of something else. Something else is this one. This is command to output transfer function. Command to output transfer function is the transfer function from here to there with this torque disturbance is 0. Okay, this is a linear system. We are assuming this is a linear system. And another one is disturbance to output transfer function. Disturbance to output transfer function. This one. So maybe this one specifies this kind of characteristics, and the other one, this transfer function will predict this kind of response. Okay, so this is the case of this DC motor drive system. Okay, so now consider our case. So small signal model of closed loop PWM converter is shown here. Okay, so this is our model, our case. So already we developed the small signal model of this and the small signal model of this, and we derived the small signal model of this, and we assemble 3 parts of small signal models all together. Then we will obtain the complete small signal model of entire PWM converters. Okay, so first let's consider this. This is the general diagram. With this connection, it becomes buck converter. If you rotate this once, it becomes boost converter. Another rotation will yield this buck boost converter. Okay, and this reference, this resistance is called output voltage controlling resistor. Our voltage control means our voltage is fixed. Okay, in the steady state. For some reason, you want to change the output voltage of your converter. This is another disturbance or another step change in the output voltage. Okay, this is the still steady state. You just control this, and you reach the new steady state, and everything settles down. Okay, so that this is different from the disturbance coming in here. Okay, so usually this is fixed, and G1 looks like this, but there are 2 choices of the controlling this output voltage. One is you adjust this one, okay, because there is a relationship between this V reference and our voltage relationship is here. Then our voltage is, it goes the downstairs of this. There is the equation of the our voltage and namely the relationship between our voltage and the reference voltage. Okay, so for that purpose, you can change this, or you can change this, or you can change both of them. Okay, which one you wanna select? Which one you wanna change? This one, or both of them? You should change this. Okay, the reason for this is the transfer function, AC transfer function from with this inverting amplifier is G2 divided by G1. Okay, there is no impact of this RX. RX does not interfere with the transfer function, AC characteristics. Okay, so even though you change this, everything remains the same. Okay, if you change this affects this. Okay, so if you change the out voltage from 5 volt to 10 volt, you should redesign everything, which is very stupid. Okay, so you should change this. This should be fixed. So this is very obvious to see, but many students, many engineers, they make this type of mistake. Okay, which is very stupid mistake. Right? You can easily see this only interfere with DC characteristics of this, like the DC regulation, and it has nothing to do with its AC transfer function. Okay, that is important, and this is fixed. Okay, this is the fixed. Fixed means this is DC. Then when we are talking about the AC dynamics, this port is shorted. Okay, this command signal is 0 always, and just redraw this, rearrange this, okay, in the form of the previous conventional feedback system, then it looks like this. Okay, this whole thing is just a print. This is a print, and this is a print, and this is the feedback controller, and this was the plus terminal is VCOM. Okay, command signal VCOM is here is 0, is fixed. And we will change this to adjust the output voltage for the given fixed reference voltage. Our voltage can be changed. Okay, so there is some relationship. This one, all right. Okay, so this is the rearranged diagram. I simply modified this to this system. Looks like the conventional control system. Okay, then this one. All right, this is a fixed. Okay, there's just some disturbance coming in. Maybe the input signal has some AC component on top of the DC component. Maybe there is just some step change in the input voltage, and same is true in the load current. Load current have some AC component on top of this component, or it will go through some step change like this. This is what? This is disturbance, not the input. Input is here. Okay, this is disturbance, and this is also disturbance. It's not the output. It's disturbance, and this VO is output. Okay, because it is located at the output side. That is not true. Okay, because it is used as the feedback signal. Feedback is derived from this signal. That signal is called output. Okay, if you derive the feedback signal from here, then inductor current is output. It's not related with the physical position of this input and output. Two different concepts. Okay, don't mix them. So this VCOM is 0. AC command signal is 0 because this is the fixed DC. So it should be grounded when you are considering the AC transfer function. Okay, and this VS and this is IO. Okay, the original handout it was VO, that was typo. So VS and IO is disturbance. Okay, I think I need S here. Then DT is control variable. Okay, this is DC is control variable. Okay, so thing is command input is invariably always fixed at this constant. Okay, when this condition is met, then output voltage is determined by this equation. I'll prove this in the next lecture slide. Okay, this is the G1. There is a G1, and this is the value of impedance of the G1, magnitude of this G1, evaluate at DC. Okay, so this is the equation. It's the same equation I introduced in the previous lecture slide. It's the same equation. Okay, this is simply rearranged in this form. All right. So the reason for that is if this becomes, oh no, it's not this stage. All right, so it will be addressed in the next lecture slide. Then only the purpose of this is to regulate this out voltage in steady state. Okay, regardless of this disturbance and the disturbance. Okay, there is no disturbance coming in. There is no command signal. So the system is basically reacting only disturbance. Okay, so very simple feedback system. All right. So this shows the output regulation against the input voltage change and load current change in step fashion. This one. Okay, VS is increased like this, decreased like this. Then our voltage will be experience the transitional overshoot and undershoot because the incoming energy is increased suddenly. So temporarily it goes above this line, but it comes back because of the feedback mechanism. Right? Same is true. Okay. The IO is increased. That means you are extracting more energy than usual. Then this will go down, and this is you are extracting less current, less energy. Then it goes this temporary overshoot. Okay, so we are only interested in this. There is no command control. There is no command tracking mission here. Okay, so output regulation. This is very easy. Okay, so whenever you see this OPM, try to set up the load equation at inverting terminal, which is this one, VO. Because this is a virtual short, so this is ground, and this virtual short, and this is no. I'm talking about DC. Okay, that is AC. Right? In terms of DC, still this is the virtual short, so this voltage V reference, and incoming current is this one, and the outgoing current is this one plus this one. Okay, this is a DC equation, and you rearrange this equation in this form. If magnitude of this is infinity, this should be 0. Okay, to make their product finite. This is the finite, obviously. Then this is the requirement. Okay. Then if this occurs at 0 frequency, then means in the steady state this becomes 0. So in the steady state we have this relationship. Okay. When we don't use this one, then output is same as the reference voltage. This becomes infinity. Then whole term reduced to the unity. Okay, this is the description of this equation at the extreme case. Okay, so this is a relationship, and this is the same relationship. The easier way is this out voltage is divided by this and this. Okay, in terms of DC, that should be the same as this is the DC equation. Okay, this is the easier. You don't have to remember this. This is very easy to see. Okay, and this never changes. There is no disturbance or no step change in the reference voltage. Okay, and the voltage feedback circuit, AC circuit, transfer function from here to there is okay. Maybe we take break here. All right, we take 3 minute break here. All right. Okay.